Hello, everyone. So last time we discussed LP duality. So the duality theory addresses itself to the study of the connection between the two very closely related linear programming model. Those are the primer and dual LPs, right? And if the primer LP is maximizing the objective function, then the dual gives the upper bound on its optimal objective function value. So similarly, if the primary LP is minimizing the objective function, then the dual gives the lower bounds, okay? And last time, we also talked about the primer and dual relationships in LP using a symmetric primer dual pair, right? Okay, so let me share my screen. Okay, so this is it. Okay, so we discussed that this symmetric primer dual pair has some characteristics, right? So the if the primer LP has m different number of constraints and n different decision variable, so the primer LP is m by n system, then the dual LP is n by m. So it does has n constraint, not including the non-negativity restriction, and m different variables. This is because for every variables in the primary LP, there is a corresponding inequality constraint in dual LP in the symmetrical primer dual pair, right? Likewise, for every inequality constraint in the primary LP, there is a corresponding dual variables. And the right-hand side vector B of the primary LP serves as the objective function coefficient vector of the dual LP. And the objective coefficient of the primary LP serves as the right-hand side of the dual LP, right? Okay, and we also talked about the in the symmetric primer dual pair. If we have an inequality reversed in the primer LP, then in the dual LP, we have the reverse direction of the corresponding decision variable, right? That's why we have here reverse direction, okay? And we also notice that the inequality of the constraint in the primary LP in the symmetric primary dual pair corresponds to the unrestricted ensign of the variable in the dual LP. So URS stands for unrestricted ensign, okay? And also we talked about the dual of the dual becomes the original primer problem, okay? So this implies that given a symmetric primer dual pair of LP problems is really arbitrary, which is referred to as the primer and which is referred to as the dual, okay? And last time we also talked about a little bit about this conversion table. So basically, dual of the LP may be found by first rewriting the given LP in the form of the one of the LP problems in the symmetric primer dual pair. But the dual can be also written directly for any LP using all these relationships, okay? So before we talked about the economic interpretation of the duality, let's consider one more example. So this is the given primer LP problem. And given this primer LP, let's discuss how we could construct the dual LP. Okay. Of course, the given primer LP is not the primer LP in the symmetric primer dual pair because it's the minimization problem that has equality and also less than equal sign. And some of the decision variables are not greater than equal to 0, right? So obviously we need some help from this conversion table for constructing the dual LP. Okay, so the given LP is 3x4 system, right? So it has 3 constraints and 4 variables. So it's 3x4, which means the dual must be 4x3 system. Okay, so if we use y variable as the dual system, then our dual LP is going to be maximization problem. And we are going to have 3 dual variables. So let's name that y1, y2, y3. And because the right-hand side vector of the primer system serves as the objective coefficients in the dual system, right? So it's going to be 20, 30, 40, and 50 in order. So our objective function is done. Now, before we talk about the constraint, so let's get the constraint coefficient matrix for the primer LP. So usually we set equal to A. So matrix A is going to be 1, -2, 4, 0. So 1, sorry, is 1, -2, 4, 0. Then 2, 1, 0, -1, right? 2, 1, 0, -1, and 0, 5, 1, 1. 0, 5, 1, 1, right? Which means the constraint coefficient matrix for the dual systems going to be a transpose matrix, right? So the first column becomes the first row. So it's going to be 1, 2, 0, 1, 2, 0. Likewise, the second column becomes the second row, right? So we have -2, 1, 5, and then 4, 0, 1, 0, -1, 1. So this is going to be the constraint coefficient matrix for the dual system. So we are going to have y1 plus 2y2, right? And -2y1 plus y2 plus 5y3 and 4y1 plus y3 and then -y2 plus y3. So those are the left-hand side of each constraint, each of these 4 constraints. And the objective coefficient in the primary system, 6, 3, 0, 5 becomes the right-hand side vector of the dual system. So we have 6, 3, 0, 5. Sorry, I'll be right back. Okay, so because the given primal LP is the minimization problem, so we need to start look at the minimization column in this conversion table. And we notice that the first variable and the third variable in the primary system has greater than equal sign, right? So in the minimization problem, the first and third variable has greater than equal sign, right? This one. So using this conversion table, this implies that in the maximization problem, the first and third constraint must have less than equal sign. So here in the dual system, the first constraint and the third constraint has less than equal sign, okay? And in the minimization problem, the second variable has no sign restriction. So here, second variable in the minimization problem has no sign restriction. This implies that in the maximization problem, the second constraint must be equation. So it's got to be equation here, okay? Let me disable my camera. Okay, a while. Okay, and so if you continue on that, the minimization problem, in the minimization problem, the fourth decision variable has less than equal sign. So the fourth last decision variable in the minimization problem has less than equal sign, right? So this implies that the fourth constraint in the maximization problem must have greater than equal sign. Okay. So we completed the constraints. Now we need to decide the sign restriction for each dual variable. In order to do that, you need to look at the sign of the primary constraint, okay? So the first primary constraint has less than equal sign, which is in the minimization problem. So again, we need to stick to minimization problem here, and then look at the less than equal constraint, right? So the first primary constraint has less than equal sign in the minimization problem, which implies that in the maximization problem, the first variable must have less than equal sign. So y1 must be less than equal to 0. Okay. Similarly, second constraint in the primer in the minimization problem has equation. So here, second constraint minimization problem has equation, which implies that in the maximization problem, right, the second variable has no sign restriction. So y2 unrestricted in sign, okay? And the last constraint, third constraint in the minimization problem has greater than equal sign, which is this. So the third constraint, the minimization problem has greater than equal sign. So in the maximization problem, the third decision variable must have greater than equal sign. So y3 must be greater than equal to 0. Okay. Okay, so this is the dual LP. Okay. Given this primer LP. Okay. Okay, now let's move on. Okay, now I'm going to talk about the economic interpretation of duality. Okay, so to illustrate the economic interpretation of the duality, let's reconsider the window glass example that has been discussed earlier this semester. So I want you to recall, so in this example, window glass company makes two glass products, right? The glass doors and windows in three different plants, okay? And the relative, the informations are summarized in this table. And because we have to decide how many door glasses and windows should be produced each week, two decision variables, X1 and X2, has been defined like this, right? X1 stands for the number of batches of the product one, which is doors, glass doors, produced per week. And X2 is the number of batches of the windows produced per week, okay? And our objective is to maximize the total profit, the weekly profit from producing these two glass products. So it can be expressed as 3x, maximizing 3x1 plus 5x2, okay? And the here each batch of doors produced per week uses 1 hour, one hours of labor time each week in plan number 1. However, only 4 hours available in plan number 1. So basically, we consider the first row to produce our first constraint, right? X1 is less than equals 4. So likewise, considering the next row in this table, 2x2 is less than equals 12. That's going to be our plan number 2 constraint. Likewise, plan number 3 constraint is going to be 3x1 plus 2x2, so less than equals 18. So we have third constraint right here. And because the production rate cannot be the negative, so we added the sign restriction in the end, okay? So both decision variables, x1, x2, has to be non-negative, okay? So considering all this together, this is gonna be our LP model for the window glass example problem, right? Okay, so let's call this our primer LP, okay? So this is our primer LP model, okay? Then the door of the window glass problem would be like this. This is very straightforward, right? Because the primer LP in our case is maximization problem with an or less than equal sign, right? So that's the dual LP in the symmetric primer dual pair, right? So our dual LP must be the minimization problem with or greater than equal sign. And of course, both side problems, the decision variables are or greater than equal to 0, okay? So obviously this is the dual LP, okay? Okay, okay, so the dual of the window glass problem is like this, right? And the first dual constraint, which is this, right? is associated with the first primary variable, which is door, okay? So X1 is the number of doors, right? Produced. Likewise, the second dual constraint is associated with the second primary variable, which is window, okay? So here, X2 refers to the number of windows, right? Produced. Also here, Y1 variable, our first dual variable, is associated with the first primary constraint, which is about the plant number 1 hours. So obviously, Y1 variable, our first dual variable, is associated with the plant number 1 hours. Okay, that is our first primary constraint. Okay, likewise, our second dual variable, Y2 variable, with plant number 2 hours, and Y3 variable is associated with the plant number 3 hours. Okay. Okay, so now you're ready to interpret the window glass dual problem. Okay, so let's suppose you're going to purchase all of the window glass resources. Okay, then obviously you must determine the price, right? You are willing to pay for a unit of each of window glasses resources. Is that correct? So to determine these prices, we need to define the Y variable. So Y1 is going to be the price paid for 1 hour of labor at plant number 1. Likewise, Y2 is going to be the price paid for the labor at plant number 2, and Y3 is going to be the price paid for the 1 hour of labor at plant number 3. Okay. And the resource prices, Y1, Y2, Y3, should be determined by solving this dual problem. Okay. And the total price that should be paid for these resources is going to be 4Y1 plus 12Y2 plus 18Y3. Because the cost of purchasing the resources is to be minimized, right? So minimizing this value, 4Y1 plus 12Y2 plus 18Y3, is going to be the objective function for the window glass dual problem. Okay. And in setting the resource prices, the prices must be high enough to attract vendors to sell the resources, right? So for example, you must offer window glass at least $3,000 for a combination of resources that includes 1 hour of production time at plant number 1 and 3 hours of production time at plant number 3, right? because window could use these resources to produce a door that could be sold for $3,000. Of course, if they wish it, right? And because you are offering y1 plus 3 times y3 for the resources used to produce a door, window must choose y1 and y3 to satisfy y1 plus y3, y1 plus 3y3 is greater than equal to $3,000. Okay. So in a way, our first constraint can be built. So likewise, at least $5,000 must be paid for the combination of resources used to produce windows. Okay. So y2 and y3 must satisfy this second dual constraint. And of course, the sign restrictions, y1, y2, y3, all of these dual variable must also hold, right? Oh, okay. And the solution to the window dual problem is the prices for labor hours in plant number 1, plant number 2, and plant number 3. Okay, so keep in mind that when the primer LP is a maximization problem, like our window glass example, the dual variable so related to the values of the resources available to the decision maker. Okay. Okay, now let's try to obtain the optimal solution for both primer and dual LPs for the window glass problem using either Lindo or Lingo, okay, software. Okay, so let me open Lingo. And let me resize the window. Okay. Okay, so the window telling me that this is going to be the Lingo input. Okay, so I'm going to use Lingo input. So our primer LP is going to be, so I'm going to put it here, primer LP. Don't forget the semicolon to end the comment. And so it's going to be maximization problem equals 3,000 times x1 plus 5,000 times x2. And then first constraint, x1 is less than equals 4. Second constraint, 2 times x2 is less than equals 12. Third constraint, 3 times x1 plus 2 times x2 less than equals 18, right? Okay. And put the ending mark and just run it. Okay, so this is our objective function optimal solution and optimal objective function value as well. Okay. Now let's run our Duality. So I'm going to put comments. Here's our Duality. Okay, that's going to be minimization problem equals 4 times y1 plus 12 times y2 plus, sorry, 18 times y3, right? And our first constraint, y1 plus 3 times y2, sorry, y3. It's greater than equal to 3,000. Second constraint, 2y2 plus 2y3 greater than equal to 5,000. And ending mark, oh, I forgot to add multiplication symbol here. Okay, so that's it. I'm gonna solve it. Now we got the optimal solution. Okay. So here's our primal and dual optimal solution. Okay. So according to the lingo output, if you look at the primal optimal solution, which is down here, we should produce 2 doors, right? X1 is the number of the glass doors produced weekly. So you should produce 2 doors and 6 windows, right? And with this combination, the company's weekly profit could be maximized to how much? $36,000. Okay. So this is obviously the seller's perspective, but when you look at the dual, which is the from the buyer's perspective, if you are planning to purchase all of Windows resources according to the dual optimal solution, the price paid for the labor at plant number 2 and plant number 3. So those 2, okay. So the price paid for the labor hours at plants number 2 and 3 has to be set equal to $1,500 per hour and $1,000 per hour, right? So in a way, we could achieve the minimum expenditure of how much? $36,000 for purchasing all of the resources from window glass company. Okay, so that's how you could interpret the optimal solution from both sides of problems. Okay, so let's go back to our PowerPoint slides. Okay. Okay, so so far we have discussed some duality properties for linear programming. And okay. Now I'm going to talk about the fundamental duality properties, fundamental duality theorems. But I know some of you are not interested in the theory. So just to let you know, my discussion on this topic will be very short. Basically, I will ignore the proofs, all of the proofs, and just read the statement of the theorem, and then provide the example for each case, okay? So again, let's consider the we consider the primary LPs in the inequality form like that. So the primary and dual LPs are symmetric. So we consider again symmetric primary dual LP like that. Okay, so the first theorem is referred to as the weak duality. Okay. So it says that in the symmetric primary dual pair, if we suppose that one problem has feasible solutions and also a bounded objective function, so it also has an optimal solution, then the other side of the problem, the symmetric primary dual pair, also has a feasible solution and an optimal solution. And it provides a bound on the optimal value of the objective function of either the primer or the dual LPs. Okay? That's what he called the dual weak duality. And simply stated, in the symmetrical primary dual pair, the objective function for any feasible solution to the primer minimization problem is always bounded from below by the objective function value for any feasible solution to its dual LP. Okay, so do you remember we discussed this using the chair and table production example earlier? So if the primary LP is minimizing the objective function, the dual provides the lower bound on its optimal objective function value. Okay. Also, as we make these bounds increasingly tighter, then the lower bounds becomes the actually the optimal objective function value of the primary LP. Okay, so that is what is called the weak duality. And furthermore, a strong duality property also states that the optimal value of the primary and dual LPs in the symmetric primary dual pairs are always equal and equals each other. So the window glass problem would be a good example of the strong duality. So how would I say? So we can say that if we have a feasible solution to the primer and also dual LPs, such that their respective objective functions are equal, then these solutions are optimal to their respective problems. So that's why the strong duality theorem is very important, because it does indicate that we may solve the dual LP in place of, or at least in conjunction with the primary LPs. Okay. Also, the second case, if one of the problems, either the primer or the dual, has a feasible solution and an unbounded objective function. So there is no optimal solution in this case, right? Then the other side of the problem in the symmetric primal dual pair has no feasible solution, okay? And third case, it is true that if only one of the problems is feasible to solve, then its objective must be unbounded over the feasible reason, okay? And the fourth case, saying that both primal and dual problems could be infeasible to solve. So we can say that if only one problem in the symmetrical primal dual pair has no feasible solution, then the other side of the problem has either no feasible solution or an unbounded objective function from this too, right? Okay, now let's take an example. So in this example, we want to construct the dual LP first, and then using the weak duality theorem to show that the optimal solution for the primal problem has to be less than equal to 0, okay? Okay, so let me split the window again in half. And this time I'm gonna open Microsoft Word. Okay. Okay, I think this should be good enough. Okay, the constructing dual would be very easy because the given LP is a maximization problem with all less than equal constraint, right? So dual must be the minimization problem with or greater than equal sign, right? And the given LP, let's say this is the primal LP. And this is going to be dual LP. So the primal LP is 2x3 system. Dual LP must be 3x2, right? So it has 3 different constraints and 2 decision variables. So let's use y1 and y2 as the dual variable. So I'm going to write it down 3 times because we are going to have 3 dual constraints. Okay. And we know that both dual variable so greater than equal sign because there is a standard primal LP, right? The symmetric primal dual pair. Okay, here right-hand side values 12, 1 becomes the objective coefficient values. -1, -2, -1 becomes the right-hand side values. And we have 1, 1, 1, 1, and 2, -1, right? Because here constraint coefficients vector for the primary system is 1, 1, 1, 1, 2, negative 1. So in the dual system, constraint coefficient vector must be a transpose matrix. So 1, 1, 1, 1, 2, negative 1. Okay. Okay, so this is our dual LP. Okay, so our first part is done. This is part A. Now, how could we deal with part B? It does ask us to use weak duality theorem to show that the optimal solution for the primal problem is less than or equal to 0. Okay, so first, let's try to get the optimal solution for the dual system. So if you look at our dual LP, our dual objective function value, let's say, is equal to Z, is equal to W, and our primal objective function value is equal to Z, okay? So we have W in here. So our dual objective function value, W, will be improved if both Y1 and Y2 decreases, right? And the lower bound of the decision variable, both decision variables, Y1 and Y2 are 0, right? Here. Because Y1 and Y2 equal to 0 satisfies all of these constraints, right? Because here 0 plus 0, which is 0, is greater than or equal to negative 1. 0 plus 0 is also greater than or equal to negative 2, right? And 2 times 0, which is 0, minus 0, that is also 0, is greater than or equal to negative 1. So this value satisfies all of the constraints, right? So this must be our optimal solution. So I'm going to put the asterisk symbol indicating these are the optimal solution value, okay? So with Y1 and Y2 equals 0, the optimal dual objective function value also becomes 0, right? 12 times 0 plus 0 becomes 0. So obviously, our dual optimal objective function value is going to be 0, okay? And the weak duality theorem tells that the objective function value of the minimization problem in the symmetric primal dual pair is always greater than, equal to the objective function value of the maximization problem in the symmetric primal dual pair. So here, our primal objective function value is Z, right? So by the weak duality theorem, we can easily show that the primal objective function value should be less than or equal to 0. Okay. So our second part, part B, is done this way. Okay. Okay. Now let's go back to our slides. Okay. Now I'm going to show you that if one of the problems, either primal or dual problem, has an unbounded objective function, then the other problem is infeasible. Okay. So this is the example problem they were gonna consider. So I also depicted the feasible reason for this case. And so our feasible reason is this side. Okay, these shaded areas are the feasible reason. Okay, so obviously our feasible reason is unbounded. Okay, so these are our feasible reason, and our ISO value line is this. Okay, so minimizing the negative function is equal to the maximizing the positive function, right? So actually our objective function is equal to maximizing x1 plus 3x2, right? So in this case, our objective function value g will be improved if we move this ISO value line in the direction for which both x1 and x2 increase. So we're going to move ISO value line this direction. So in a way, your x2 value will be increased and x1 value will be increased, right? So you need to move the ISO value line this way, okay? This direction. Now, of course, the objective function will continue to improve the further away from the origin into the unbounded region, right? So obviously, this given LP is unbounded, okay? Then the other problem in the symmetric primal dual pair is like this. So that's going to be the maximization problem with less than equal constraint, okay? And wait. Oh, I see. Because the given LP is the minimization problem with less than equal constraint. Okay, so we talked about this case earlier, right? So if you have an inequality reversed in the minimization problem, so actually in this case, two of them, right? So actually this must be less than equal sign. Sorry, this must be an error. Okay, so here we talked about this with an example earlier. In the symmetric primal dual pair, if you have an inequality reversed in the minimization problem, just like that, then it's dual problem, which is maximization problem, must have reverse direction of the decision variable. So this must be the correct answer. Okay, so y1 and y2 both must be less than or equal to 0. Okay, that's why we are considering this quadrant. Is that the third quadrant, right? So we need to consider this side. Okay, and you know what? These two dual constraints are never in agreement in this third quadrant. So actually this problem, this dual problem, has no feasible reason, which means that this dual problem has no feasible solution. Okay, so this case is infeasible. Okay, so that's the second case of this fundamental duality theorem. Okay, next example will show that if the primal LP has no feasible solution, then dual LP has an unbounded objective, actually. So, okay. So in this case, the feasible reason is empty. So it contains no points, right? Because no points satisfy these both constraints. So there is no feasible solution, right? Because there is no feasible reason. So there is no feasible solution in this case. So it's infeasible LP. Okay. So this is infeasible. Infeasible LP. Okay. And the dual LP is like that. So in this case, our feasible reason is here. Okay, because the origin does not satisfy both of these constraints, right? 0 plus 0 is not greater than or equal to 1. Also 0 plus 0 is not greater than or equal to 2, right? Which means this origin cannot be the feasible point considering these two constraints. That's why the feasible reason should be here, up here, okay? So the feasible reason should be the points above these two lines, right? And the line itself, okay? And let me change the color. And our isovalue line would be this one, okay? And in this case, our objective function value, W, will be improved, will be decreased, right? So we want to minimize the objective function, right? So our dual objective function value, W, will be improved if we move the isovalue line in this direction, right? So that Let's say next isovalue line would be something like this. So in a way, y2 value has been decreased, right? But your y1 value will be improved, increased, okay? So if you extend this, you can easily see that, right? Y1 value has been improved. If you move isovalue line from here to this direction, right? Like that. So the thing is, objective function value will continue to be improved the further away from the origin into the unbounded region in this case. Okay, so this is so this is one of the constraints, right? And isovalue line can be drawn this way. Okay, so which means that our objective function value will continue to improve the further away from this region, okay, into this unbounded region. So obviously here the objective is unbounded, okay. So this is a good example of the case. If only one of the problem is feasible, then its objective must be unbounded. So because the primer LP is infeasible to solve, the dual LP in this case is unbounded. Okay. Okay, and the next example will show that if the both actually in this case, let me see. Okay, if the primary LP has no feasible solution, the dual LP also has no feasible solution. So it is telling you that the both primary and dual problems can be infeasible, okay, at the same time. So here's the given primer LP, and this is our dual LP, okay. And obviously, the feasible region for the primary LP contains no point because no points satisfy these two constraints. So it's infeasible. LP. Okay. Likewise, our dual LP has no feasible reason, which indicates that dual LP is also infeasible to solve. Okay. So we can say that if one problem in the symmetric primary dual pair has no feasible solution, then the other problem has either infeasible to solve or has an unbounded objective function values. Okay. That's from these two properties. And okay, I'm gonna stop here for today. And actually, I was going to talk about the complementary strengthness theorem, which is another very important theorem in LP duality. But I'm going to talk about that next time. And we're going to give you some example problems for that as well. Okay, so I will stop here for today, and we'll see you next time. Thank you very much. Bye-bye.